I'm going to go ahead and record this on the video just so that you have the explanations, because if you miss something, then you can go back and play what I said about the Kahoot questions, because there'll be some I'm sure you're going to miss because I was tricky with some of the answers. And very specific. So the code is 758541. Is that everybody? Looks like it. Okay, so which atomic orbitals are involved in bonding in chlorine 2 or Cl2? So the red is 1s orbitals, the blue is 2s and 2p, 3s and 3p is orange, and all of these is green. Okay, it's a 3s and 3p. I put this one in there just to emphasize. I saw some people on the last time doing MO diagrams where they use the 2s's and the 1s. No, no, no. The 2s and the 1s orbitals and the 2p orbitals are core electrons, and core electrons do not participate in bonding. Okay, it's only the valence electrons. Okay. The crystal field, when we talk about that, it defines what? Does it define the point group symmetry around the central atom? Does it define the magnetic field around the central atom, the electric field around the central atom, or the shape of the crystal? It might affect all of these, but what are you using it for? You're using it to find the point group around the central atom. So if we put a metal atom in an octahedral crystal field, we have 6 identical things around it, then that's going to be an octahedral point group. So that's what we mean by crystal field. What's the point group around the metal? Okay. Internal conversion involves a change in what? Potential energy surface, multiplicity, or both? Potential energy surface only. So internal conversion, there's no change in multiplicity. It's intersystem crossing. Yeah. Which does it involve? Yeah. Yeah, exactly. You should not miss that. That's 5 easy points on the test. It's both. Okay. You change potential energy surfaces and you flip a spin. Okay. So 5 easy points for 5 people. Okay. So then which of these is a radiative transition? Intersystem crossing, internal conversion, fluorescence, or phosphorescence? Pick the one you're most confident in. It's either fluorescence or phosphorescence. Both of those are correct, okay? But not intersystem crossing, not internal conversion. Those are non-radiative. Those are just hopping from one potential energy surface to another. A laser requires a blank. A thermal population, a population inversion, a short lifetime in the upper state, or a continuum of absorbance. Good. It's population inversion. The other options, thermal population is exactly not what you want, okay, because that's mostly atoms in the ground state. Short lifetime in the upper state, that makes it difficult, actually, because you want to have molecules get stuck in the upper state. So you really want a longish lifetime in the upper state. And then the continuum of absorbance, we're dealing with individual energy levels, so a continuum is a smear of energy levels. It absorbs at all wavelengths, and so you really wouldn't want a continuum of absorbance. Why does an exiplex always have a population inversion? Because the efficiency of the pump transition, because of the ground state doesn't exist, because it's in the UV, or because it has a thermal equilibrium, because it's at the thermal equilibrium. Great. So it's because the ground state doesn't exist. The exi part means excited. So exiplex is an excited complex that only exists in the excited state, and an eximer is an excited dimer. So eximer or exiplex, both are only existing in the excited state. Which atomic orbitals are involved in this bonding MO? Yeah, which atomic orbital? So we have options. The red is px, py, pz with the ligand s orbitals. The ligands are the things on the outside. dxy, dyz, dxz with the ligand orbitals. It's the blue. The d 2z squared minus x squared minus y squared with the ligands. I ran out of time. Okay, it's this one here. Let's look at the picture. Yeah, time ran out. Okay, do you see? It's the z squared minus x squared minus y squared. So that's the dumbbell with the donut. And then that's in phase with the 1s orbitals on all of the surrounding atoms. So let's try this one. Which atomic orbitals are involved in this MO? Px, py, pz with the ligand s orbitals. dxy by itself. The dz squared with the ligand s orbitals, or dx squared minus y squared by itself. And the axes go along the atom bonds, just for your information. Okay, so it could have been this one, but like I said, the axes go along the bonds. And so this is, let's say this is the x-axis, and this is the y-axis. Notice the lobes are in between. So it would be the dx times y. So if I take x times y in this region, I get positive. I take negative x times positive y, I get negative. If I take negative x times negative y, I get positive again. And if I take positive x times negative y, I get negative. So you see how it changes sign in that plane of plus minus and between the axes. What is the point group symmetry of this crystal field? So this molecule, forget about the orbital, just the molecule itself. You've got a metal surrounded by 6 identical things. Whenever you have 6 identical things around a central atom, it's what point group? It's octahedral. Okay. C2V would be something that looks like water, right? The left and the right side are the same, the front and back are the same, but the top and the bottom are not. Okay. What is the point group symmetry of this crystal field? Okay. Ignore the stuff on the right. Just look at where the atoms are. Also, ignore the orbital. Just look at the atoms. Central atom, 4 identical atoms around it. Yay, I love to see that. Okay. Yes, an atom surrounded by 4 identical things is tetrahedral. What if it's 2 and 2? So like Cl2H2, so dichloromethane. The chlorines and the hydrogens are not the same thing. So what does that have to be? C2V. Yes, C2V. And you can draw it like this. You've got the chlorine, the carbon. Let's draw it like this. They look the same, don't they? Yeah. So C2V. By comparison is a great way to do these different ones. What about Cl3H? Looks like ammonia. Very good. Let's do ClC down here. Looks just like ammonia. So C3b. Describe this MO. Is this one bonding, anti-bonding, non-bonding, or all of the above? How can you tell? It's non-bonding. Let's look at the picture. Do I see any electron density between any of the atoms? Right? Here's a hydrogen, there's the metal, there's no electron cloud between us. So it's not contributing to the bond. It's not anti-bonding either. I don't have electron clouds that are out of phase where the node would break the bond. It's just the nodes are along the bonds. There's really no bonding character to that. Yes?
So are the green regions connected in the molecule? Because I thought that was antibonding because it looks like there were nodes.
Well, there are nodes, but they're kind of along the bonds. They're not breaking the bond. So if you want an antibonding orbital, you would have a node that breaks the bond. Like 90 degrees to the bond. It cuts through the bond. Let's look at this next one. Describe this MO. And then that'll be it for today. Is this bonding, antibonding, non-bonding, or all of the above? I'll tell you now, all of the above is a silly answer. Although I guess you could have it bonding for some things and antibonding for others and non-bonding for others. So maybe it's not so silly. Yeah, so this one's bonding. Look at the picture. You see between the hydrogens and the metal, there's electron cloud. There's electron density. Okay, so if those lobes absorb those bonds, then they're helping the nuclei, which would repel each other, stay together. Okay, do you see that? Okay. And then if those electron clouds change sign along the bond, meaning there's a node that cuts the bond, that'd be antibonding. Okay, good job. And you can log into Kahoot, create an account, and look for Kim_prof to find all my Kahoots so you can practice. That'll really help you review for the final.
My phone cut out the Kahoot, the last couple questions. Did I still?
You'll get credit for taking it, yeah.
Okay, I just wanted to know if my name was still recorded as participating
yes, it
or
will.
not.
Yeah, as soon as if you log in at all and like just get one question, then you'll be marked down as participating. Good question.
Same thing that happened to her.
If you got in at least one question, then you'll be.
Oh yeah, I was there for like most of it. It's just
good. Yeah, it was a long one. Go ahead. Yeah, you're fine. Yes. Yeah, I've got them all right here if you want to wait till I get shut down here. Tomorrow? Yeah.
Can I swing by? I have a meeting at 11. So I'll swing by at like after 12 or
Tomorrow. I don't know yet. I can look at my calendar. Yeah. Let's see.
but if I came at like 1-ish, but
Yeah, I'd probably be okay. Yeah. But shoot me an email and I'll tell you specifically.
I did.
Very much. You got your
I got mine. I don't disappoint that, but.
Good, how are you?
Good. I'm going to stop you at 2.
Okay, fine.
What do you need to try for?
Video camera, yeah, so I
Uh-huh.
record the board sometimes when I do work on the board.
Oh, okay.
This has been